Hello everyone. Uh, Welcome to your own channel Paper Money, and I am Biplab Datta, and I am teaching you quantum mechanics. This is the 24th lecture. So we had discussed in the previous lecture. We started discussing the quantum mechanical step potential, and we'll take it further today. So we had. So this is continued from previous lecture. So we have this step potential, which we have been discussing so far. Now, whatever I am discussing is all quantum now. I'm not mentioning it separately. All right, so step potential, and this is continued from previous lecture. All right, continued from previous lecture. Now, let's see what we had like solved one of the cases, not completely, but we had some results. All right, so let me make a straight line. It looks good. Okay, it will do. So we had this expression in region like if we were discussing case where this was E greater than V naught. All right, and the wave function which we got for region 1. So this is from previous lecture. I'm writing it down, summarizing it. So region 1, we had this wave function which is equal to A E I k x plus b I minus I k x. All right, and x is less than 0. Okay, so the region 1 is x less than 0. Now in region 2, what happens? Now region 2. All right, so region 2, let's write down the time independent Schrodinger equation. Time independent Schrodinger equation. All right, so in this region, this is x greater than equal to v naught 0. So we have this thing that vx is equal to v naught. All right, in this region we have this situation. Now let's plug this in the Schrodinger equation. All right, so this is minus h cut square by 2m, and derivative with respect to x, and we have this v naught psi 2 is equal to e psi 2. All right, we have this equation. Now just let's solve this. So in this case, what we have is d double derivative with respect to x of the wave function plus, let's rearrange this thing and write it like this. So we'll do some rearrangement. So this will give us e minus v naught psi 2 is equal to 0. All right. Next, what we do is we simply like just substitute one thing, which is we'll substitute another k which belongs to region 2. Now in this case, we'll put in k1, okay, and this is psi 2 equal to 0, where k1 is the wave number in the second region. Okay, so this is e minus v naught by h cut square. All right. Now this will have the solution to this equation will be the following. This is psi 2 c e to power, this will be e to power I iota k1x plus d e to power minus iota k1x, where x is greater than equal to 0. All right. So this is the wave function in this region, in the second region. So let's mark it. All right. Now there's one thing that whenever we do experiment, like we hear about the particle accelerator, where a beam of particles are sent to a target atom or a target nuclei, and then they see what all nuclear reactions occur. Okay. In the scattering experiment, so this is also a scattering. Okay. There is no bound state, so the potential is not an attractive one. All right. So it's a scattering experiment, so we are sending the beam of particles from one side. So in this case we are sending it from the left side. Okay, if you remember the figure, we were sending the particle is coming from the left to right. Okay, and there is no particle coming from right to left, because we are not we means we are not sending any beam from right to left. Okay, there might be reflections, that is another thing, but then we are not expecting any particles in region 2. Okay, in region 2 coming from right. All right. So in that case, because the potential does not change once the potential shoots up to v naught, after that there is no change in the potential. Okay, it remains constant. All right. So there is no chance of reflection. Okay. If there is a change in potential in anywhere further than that, like either it goes down, either it goes up. Okay, the value goes up. So it will reflect. It will have some reflection. Okay. But in this case, once the potential becomes like constant, it remains constant. In our case, the toy problem which you are looking at. So this is a toy problem. Okay. This might be approximately uh, give you some answers, some results to you can use this model to approximate some experiments, but not all. Okay, in reality there will be a variation of potential as you go into the other region. All right. So let's write down this conclusion that in region 2, in region 2, all right, which is x greater than 0, x greater than equal to 0. Now in this thing, the potential remains constant, remains constant. Okay, it does not change further. All right, neither it decreases, neither increases. All right. So in this case, also the incident beam, the incident beam, the incident beam is from left to right. The incident beam is from left to right, is from left to right. All right. Now, so there can't be, so there there can't be any reflected wave. Okay, any reflected wave in this region. All right. So see, we know this from our previous analysis that this quantity, this exponential, this function represents a particle moving with momentum h cross k1 along the positive x direction, and this one, okay, let's mark it with something else. So this one was for particle moving from like particle moving with momentum h cross k1 along positive x-axis, and this one we found that this has a momentum minus h cut k1. All right. and it is since the momentum is negative, now momentum is a vector, all right, vector quantity. Now this represents that this wave function represents a particle moving towards the negative x-axis, all right. So that means in this region, this component should not be there, okay, since there is no reflection possible, or there is no incident beam, all right. So d should be 0, d should be 0 to, because we want the physical, the mathematical representations of wave function to match the situation we have modeled, all right. So let's see what is the now final wave function in this region 2. Final wave function in region 2 is equal to e to power I iota k1x, which is x greater than equal to 0, all right. So this is the wave function which represents our situation for the given model, which is the step potential. All right, so we have written down both the wave function in region 1 and 2. Now let's write down the complete wave function. Okay, let's write down the complete wave function. Okay, let's see how does it look. So the complete wave function, complete, when I say, it means that we are adding the time factor. We have not yet added anything related to time yet. So what we have to do is just multiply the exponential factor, which includes time, to these wave functions, and we'll get the complete wave function. So if we write down psi of xt, all right, so this will be, so we have two parts, which is psi 1 xt for the region 1, all right. So in this case, a iota kx, now the time is time part is minus I omega t. Now I write omega we know that we have this thing. The time part was like this, right? If we recall, we had this psi xt written like this, some c constant, and then xt, and exponential iota et by h cut. Okay, this is what the result was, and we can replace e by h by omega. So we know that E is equal to h cross omega, and omega can be written as E by h cross. All right. So we are using this thing, and we are replacing. It's nothing. It's not that it cannot. You can write it in energy also, but in this thing, it's customary to write it in omega format. All right. So nothing so significant to talk about. So in this one, so we have minus I omega t. All right, so this is the form we get for the complete wave function in region 1. Now this can be further written like this, that iota kx minus omega t, all right, plus b, okay, plus b e to power minus iota kx plus omega t. Right, now this is for region 1, which is x less than 0. This is one of the wave functions which we have written in complete with along with the time. Now the other part is psi 2. Okay, so this is equal to c e to power iota. Okay, let's write it directly. So we'll get k1x minus omega t. All right, so this is the complete wave function we have for the whole system. All right, now let's interpret few things here. Now what does it represent? Now this part, which is a e iota kx plus omega t, now this represents an incident wave moving towards positive x-axis. All right, represents an incident wave moving towards positive x-axis.
माइनस आएगा उसमें ऊपर.
Sorry, there will be a minus sign. Yeah, you're right. You're right. And the next one is b minus iota kx plus omega t, and this represents a reflective wave, represents a reflective wave moving towards negative x-axis. All right. So this is, you have done similar things in wave mechanics. All right. You should recall that this is the phase part which we have here in the exponential part, and you also understand this thing that the way it's represented in wave form, that if you have two different signs for k and omega, then in that case, what happens, the wave is moving forward along x positive x direction, and if there is a opposite signs, like same sign on k, this part and this part, then that represents a wave moving towards the negative x-axis. All right. Now let's talk about something. Now in this case, when you do experiment like scattering, where you have a lot, like many particles in the beam, and it's difficult to track each of them, so what we do is, instead of tracking the particle number, what we do is we take a cross section, let's say perpendicular to the beam, and we try to get the flux measure, like the number of particles which are passing through the unit cross section area per unit time. Okay, so that gives us a measure of like what is the number of particles in the beam. All right. And so for that, to measure, for measuring the flux in of the beam, we'll define a quantity called probability current density. Okay, so probability current density. So if you can recall from EMT, electromagnetic theory, like you can derive this thing, that if you have say a charge distribution, if you have a charge distribution, all right, and this is say rho, rho is the charge density, all right, of this thing. So, and there is a flow of current. Okay, there is flow of current. This is say a volume charge density, you can think of it like that, and the flow is the current. Okay, current density. Now J is, now this is the example I'm taking from EMT. Okay, just to show you a comparison, you can also see a similar situation in so let me completely write this. EMT is not a universal, so this is electromagnetic theory, electromagnetic theory. All right, so in this case, what we have is, we are not going to derive this thing, but I'll state this as it is, that the rate of change of charge density, like if the charge is flowing from some inside some volume, going outside, so the rate of change in volume density, okay, is equal to the, okay, the divergence of J. All right, so how much it's like flowing out. So these two are related. Okay, now this is called the local conservation of charge. This equation is called, it comes from local conservation of charge. All right, and if you write this down, just rearrange this thing, and we get d rho by dt, which is equal to 0. Now this is the continuity equation. Continuity equation. All right, so this is called the continuity equation. And this negative sign, you can see this thing, if this negative sign occurs because this quantity is positive on this side. So this is positive because J, we have taken it to be flowing out, like outside, like outward. So this quantity will be a positive one, and this quantity, this d rho by dt, since it's reducing with time, okay, we are assuming that the charge is flowing outside the volume. Okay, so it's reducing with time, this means this will be negative. All right, so that is why we have a negative sign here, to compensate for this negative sign, so that both sides are equal. All right, so this is how we can understand this situation. Now in this case, what we have is, the rho is the the rho is the charge density. It is a, you can think of it as a volume charge density. Okay, and J is the current density. All right. Now there is same similar situation in fluid mechanics also. If you have studied fluid mechanics, you get the same continuity equation, but for different thing. It is related to the mass, flow of mass. All right. So we'll not get into that, but just to give you an idea how to think of how to think of the probability current density, I just gave an example of this. All right. Now let's see how can we treat the probability like a flowing quantity. Like now somebody came up with this idea that we can treat we can treat probability we can treat probability as something which flows, as something which flows, okay, like a fluid or like a charge. Now let's see how what does it mean. So if we have a situation where say let's take a 1D box, let's take a 1D box, okay, and in this case if you have this thing that now let's take this example, and this is infinite, this side is infinite. All right, now this is 0 to L. All right, and we have this situation where say the wave function somewhat looks like this, like it could be a superposition, it could be anything. Let me draw it like to make more sense. All right, so just a rough drawing. Okay, it could be a superposition thing, anything, it could be anything could be possible. Now v is 0 here. All right, so this is the say the wave function at any time t. This wave function is at any time t. Now let's say after some time this changes to this situation. After some time the wave, let's draw the potential well first. Okay, so this is say it becomes like this. Okay, it becomes like this. All right, the shape changes. Okay, now the probability, now to the probability in this part say increases, and in this one it decreases. All right, earlier the probability was higher on this side. Let me draw it to it so that the example is more significantly clear. Now what happens is the probability distribution changes after some time. So this is a psi mod square at some later time. Okay, now this is also a Vx is infinity and Vx is infinity, and this is 0 to L. All right, now after some time this change is after some time you are observing the wave function. Okay, and this changes. All right, the shape changes. Now what is happening here? Why are we treating it to be that the probability can be treated as a some quantity which can flow? All right, now this thing that the total probability, whatever the wave function be, whatever the probability distribution be, but one thing remains constant: the total probability of finding the particle, of finding the particle, okay, inside the box. Okay, this is the box, potential box, is always 1. So we can say the probability is conserved. The total probability is conserved always, because the probability of finding the particle is always inside. It's always inside the box. It's not going anywhere, but the distribution changes. Okay, so it's like a charge where like it's flowing outside, but the total charge in the whole system is constant. All right. So this is kind of some in rough, it's some kind of conservation of the probability. All right, so we'll have similar equation, similar continuity equation in this case also. We'll derive it and see. All right. So you don't need to remember the derivation, but you need to understand how things are happening. Okay. So that is how you can get a deeper understanding how to look at things. All right. So I'll be discussing derivations which are important from your exam point of view. Okay. Because questions are asked from the derivation. All right. If something is changed, some parameter is changed, what will happen? So that is why I'll be doing some derivations in the course, and those derivations which are not required in the exams, I won't be doing it. All right, I'll just state it as it is. Now the Schrodinger equation, now we'll derive this thing. So we'll derive the probability current density. So probability current density derivation. All right. Now in this case, we have the equivalent. Now everything we start with is a Schrodinger equation here, at least at our level, whatever we are discussing, whatever syllabus we are covering. Now, but we'll see that in while we can solve this harmonic oscillator problem without getting into a Schrodinger equation. So that is also sometimes a possibility that you don't need the Schrodinger equation at all. So let's write down the this thing, the Hamiltonian. Okay. Now this one is psi xt plus Vx. All right. Now psi, this is psi xt is equal to iota h cross L psi. This is x t, and say this is equation one. All right. Just wrote down the Schrodinger equation. Okay, using the complete wave function. All right. Now this thing, the taking the complex conjugate, taking complex conjugate. Why are we taking complex conjugate? Now the probability is related to psi star psi, the probability density. Okay, the probability density is related to psi star psi, so we need psi star. Okay, so that's why we are doing this thing. So you can write it down for reference, that why are we taking this step, why are we getting the psi star. We are getting it because the probability density is psi star psi, okay, which is psi mod square. So we need a psi star. So let's take a complex conjugate. Now take a complex conjugate of equation 1, right? Of equation 1. All right. So let's write this down. So if you take a complex, now these are constants, so nothing will happen to them. The derivatives will remain as it is, but just the function will it will take get a conjugation sign on the top, and this is v is a real here. Okay, we are assuming that v is real here. All right, v has to be real because it's a real physical quantity. All right, wave function can be complex. Now this is psi star x t. All right, so this, let's say, equation 2. So we got the psi star from this equation. Now what we do is, now just to get this thing, that we want psi star psi somehow, so we'll multiply this. Now we'll do some multiplication. So multiply equation 1 with psi. All right, with psi, and equation 2 with psi star. All right, equation 2 with psi star and equation 1 with psi. Did I make a mistake here? Yeah, I made a mistake. Actually, this should be reversed. So this is equation 2, this is equation 1. Okay, so if we multiply, so what we get is, we get the following thing, that uh, minus h cut square psi, this is a derivative, this is psi star divided by, this is derivative with respect to x, and we have psi, and psi star equal to minus I h cut psi. All right, and we have this derivative here with respect to time. All right, just a simple multiplication. Now let's label it 3. Okay, and the next equation which we get from this thing is psi star. Now this will be derivative with respect to psi. All right, plus Vx and psi star psi is equal to I h cut psi star psi t del psi t. All right, so this is fourth equation. So we have a combination here. We have a psi star and a psi. All right, so we are very close to the final situation. Now in this case, we need to get, we just, it's a two equations are there. We have to solve it and get the value, get the value, the term which will consist of psi star psi. Now what we do is we subtract equation 4, we subtract equation 4 from equation 3, from equation 3. All right, so what do we get? So this is the equation you'll be getting, that minus I h cut, and this is psi star del psi t, okay, plus this psi del psi star, this is del t, all right, equal to h cut square by 2m. All right, and we have psi derivative with respect to all right, so this is the expression which we get if we, when we subtract things. So we get rid of the potential term because it's the same thing. Psi star is equal to psi star psi is same as psi star. All right, so we get rid of that potential term when we subtract, and we get this final thing. And this is the uh, if we rearrange, if we do some simplification, and then we get this thing I h cut. Now we can represent this thing, this quantity, okay, this quantity as derivative with respect to time of psi star psi. Okay, we can club them together. That's the way, just reversing the thing that we have this thing, that derivative, if you take a derivative of u and v, so you get u dv by dx plus v du by dx. So we are just using it in reverse order. All right, we are just getting it back. We are, if you differentiate this, you can get this. All right, so now this is equal to h cut square. Now we can take this common. So we have psi derivative with respect to x minus psi star derivative with respect to x of psi. All right, so this is the equation which we're getting. Now we have the thing which we are looking for so long. The we are just writing this as p. Okay, p is the probability density. All right, now rearranging this thing, we get this constant outside, and we have this situation. Sorry, it's the same thing as the previous one. We're just writing it down. This term remains the same, just the constant changes outside this bracket. All right, so you have this derivative with respect to x minus this psi star, and derivative with respect to x square. All right, so second derivative. Okay, so let me make this bracket a little more nicer. Yeah, so this is, now we have arrived at what we were looking for. We have the rate of change of the probability density. Okay, now if we write this down like this, if we can just rearrange a little bit further, we can write this as, we can, okay, we can write it like this. We can get rid of the double derivative. Okay, if we, now I'm writing it directly here. Now this is double derivative is not there anymore. Okay, let me make the correction. There is no double derivative remaining. Uh, we can expand this. I'm directly writing it here. So this will be, so you can if you take the derivative, you'll get back to this result. All right. So this is what we have, and then again to just, so there is a convention which is followed. So we'll take it there. So the convention is to have a negative sign outside. All right, and we have this rearrangement. This is derivative. Now the terms are exchanged because we have taken a negative sign outside. All right, terms are exchanged the because we have taken a negative sign outside. Now this is the format which we want, and this is defined as the derivative of j. Okay. Now what is j here? Now this is in 1D. We have solved the whole equation in 1D. Okay. We did resort to 3D. You can also do the derivation in 3D. Now in 3D, this will become, this is minus, and now this is a kind of a gradient here. Now in the 3D, it will have this divergence thing. All right, we'll take a divergence here, and this is what we were looking for so long. Okay, so if you compare this with the previous equation which you wrote for the charge continuity equation, okay, so in that the form is same. All right, the form comes out to be the same, and it's very like sometimes very uh, interesting to note that we have the same equation across all so many different physical quantities, okay, which we have defined in different subjects. So in 1D, let's write down the final form of j. Now here p is the probability density. The p is the probability density, and j is the probability current density. Probability current density. Okay. All right. Now in 1D, we have j is equal to h cross by 2m iota. All right, h cross by 2m iota and 2m iota, and we have psi star del psi by del x minus psi del star, this is by del x. All right, so we have this in 1D, and in 3D, we have j vector is equal to h cross by 2mi. All right, now psi star del psi minus psi del psi star. All right, so this is the final form of the current density, probability current density, which we are looking for. All right, now let's write down some few points. How do we interpret this current density? All right, so the magnitude of j, the magnitude of j vector represents the flux of particles, that is number of particles, number of particles, okay, passing through a cross section, okay, uh, passing through a cross section per unit area, per unit area, per unit time. So this is this is a similar description of J which we had in electromagnetic theory. That in that case, in electromagnetic theory, J represented what? It represented the current flowing through a cross section. Like if it's a three dimension, in three dimension, it is the current flowing through a cross section area. All right. So in 2D, it becomes this thing that current flowing through across a line. All right, perpendicular to it. Now, so it's a similar description here. So of the direction of probability current of probability current density of probability current density is along the direction of flow of particles. Okay, so this is the direction of J. So the direction of J is along the the direction of flow of is along the direction of flow of particles. All right. So this is what we have here. And let's take an example and to understand what we are looking for next. So for example, if we say we have 10,000 particles, okay, this is not like it's a different thing which I'm discussing next. It is the reflection coefficient and transmission coefficient. Okay, so what do we actually measure in a scattering experiment? Okay, so that is what we are going to talk about. So if say 10,000 particles were sent in the beam, if there were 10,000 particles, then say after in the experiment 4,000 are reflected, okay, and 6,000 transmitted. 6,000 transmitted. All right. So we talk about this thing, that reflection coefficient. Okay. So reflection coefficient is equal to 4,000 by 10,000. All right. And transmission coefficient. So it's kind of measure of some kind of it's a kind of a measure of probability that how many particles are passing through and how many particles are reflected from the scattering potential. So in this case, the transmission coefficient becomes the number of particles which are transmitted divided by the total number of particles. Okay, so just a rough like a simple example how to think of these things. Now, uh, the reflection coefficient in this case, which we have been dealing with, is the step potential. So we define this thing, the reflection coefficient. Okay, the reflection coefficient, or these are several names, or reflectance. So examiners could use any of the names, or reflectance. Okay, or there's another name, reflection probability. Reflection probability. So all these mean the same thing. Okay, so any one of them could be used. So let's define it. So this is the reflection. It is defined as the mod of reflection probability current density. Probability current density. Current density okay, and divided by, this is incident probability density. Incident probability current density. All right. Now this is written as further JR, which is the incident reflection probability current density divided by the JI. All right. Now this is how we measure probability reflection current reflection coefficient in this case. Now this is a point you should remember. So I'll highlight this thing. Okay. So whenever we talk about the reflection coefficient, it has to be the ratio between these two quantities, or the magnitude of these quantities. All right. So you should keep this in mind. And now these are the mod signs. These are the mod signs which I have drawn. Let me make it bigger. Now these are the mod signs. Okay, modulus. So this gives you the magnitude of the quantity. All right. Now let's see what happens. What are the probability densities in each of the cases which we have described earlier. So incident wave. So incident wave. Now the probability density does not depend on the time or a time factor. It does not depend because we have seen this earlier also. Now these are also stationary states, ikx and minus ikx. If you even if you add the time part, the probability density is not affected. So what we are we are looking for is trying to compute the probability current density using the only the space part. Okay, you could have used the time part also, but it wouldn't make sense. All right. So this is kx. All right. Now let's talk about what is the probability current density of the incident wave. So just use the formula which we have, 2mi. Now what was the formula did we write here? This was, yeah, we had written like this. So see, although we had taken this minus sign just because we wanted to represent it as, because there's a, if something is decreasing, if probability density is decreasing somewhere, then it has to increase somewhere. All right. So and it should be represented by this thing that here also the same thing, the sign here is a negative. All right. Let me write it down separately. All right. Mm. So I've already discussed this equation, so I don't think it's required anymore here. It's the same thing which we have discussed here in the charge case, why the sign negative appears. Okay, it's the same thing. Now, if we have this thing that, let's calculate the probability density for this, that is ji h by 2 mi. Okay, so we have psi incident. Okay, now this is del psi I del x minus psi I del psi I x. All right. So put the value of psi. Let's put the value of psi and see what is the current density associated with this. So put value of psi I. So this is j incident equal to h cross by 2 mi. All right. So if you calculate this, so from this what we'll have is we get a, we can take out this thing a mod square because there is a psi star and there's a psi. Okay, so a is a real a is a complex number. It could be a complex number. All right, so this comes out to be outside, so this becomes a mod square. All right, and what we have inside is iota k plus iota k. All right, because if you take, because psi iota not iota psi I is equal to a e I k x, and if you have psi I star, this is a star, and they will conjugate, so this will become this. All right, so these are the psi I and psi I star, and further we have this situation that we have h cross k by m. All right, and this is a mod square. So it represents, so it is like this is the h cross k is the momentum, right? H cross k by m. So if you divide a momentum by m, what should you get? The quantity will be a velocity.
Velocity.
Okay, so velocity multiplied by this thing, which was the number of particles this thing per unit length. Okay, so if you multiply that, you'll get the flux, right? So you can think of it that way. This is some kind, this is a velocity, all right? This is a velocity multiplied by the this a square, and we had the a square meaning. So this is the velocity, okay? And this part is the momentum. This yellow part is the momentum, right? This is momentum. Now momentum by mass gives you the velocity, and if you just think of it like this, whenever you try to calculate a flux in even in thermostats also, okay, like, or in you can talk about any situation where you have where you try to calculate the flux passing through a cross section, okay, uh, per unit area, you you have a similar looking equation. Okay, so you have a velocity multiplied by the this thing, the number of particles per unit length, or per unit area, or per unit volume, depending on which dimension you're working with. So this is the and this thing we had already written down yesterday, that this interpretation was number of particles. Now number of particles is already like connected with the probability. Okay, so number of particles per unit length. All right, per unit length. So it basically boils down to whatever we wrote about J. Okay, we wrote the magnitude of J as the number of particles per crossing per unit area per unit time. So that is what it is. Okay, so per unit area per unit length. What is happening here? Per unit length. Now, if you multiply these two quantities, sometimes this software does not behave as expected. Per unit length. All right. So if you multiply this thing, if you multiply the velocity as meter per second, okay, so in that way, like, it comes down to the same thing which we already defined. All right, so let's talk about now what can we say without doing the calculation. What can we say about the reflected this thing, probability density? How can we write it? So it will have, of course, the momentum is reversed in this case, so it will have a negative sign in the momentum part. Mass remains as it is, and what will we get here in this thing? The reflected part was what was, this is b e to power minus iota kx. Okay, this was the reflected part. So instead of a, we'll get here b. Okay, so the reflected probability current density, you can directly write it. We don't need to work down the, we have already worked it out once. So just look at the form and then write it down. Now, what is the probability current density of transmitted wave? Now, this is the probability current density of the reflected wave. Probability current density, probability current density of reflected wave, of reflected wave. All right. Now, so what is the reflection coefficient? So reflection coefficient reduces to this form. Reflection coefficient, or reflectance, all right, or reflection probability becomes JR. This is J incident is equal to B mod square. So by A mod square. Now you can see that it reduces to, now this one is also the number of particles reflected per unit length. This is the number of particles incident per unit length. Now the examples which we took, the simple example, in that case we didn't talk about the number of particles per unit length. We just talked about the number of particles, the 10,000 particle example. Okay, so in this case also it boils down to the same thing. You have this, the if you have per unit length here also, if you have per unit length, the both those quantities cancel out, and what we are left with is the number of particles. Okay, so since it's not easy, like it's not easier to like calculate this thing during an experiment. So what we resort to is the measuring the probability current density. Okay, and finally we get the same thing which we had discussed in a simple example. All right, basically it reduces to the number of particles getting reflected and divided by the total number of particle incident. All right, so let's talk about the probability current density of transmitted wave. Probability current density, current density of transmitted wave, transmitted wave. All right, now this transmitted, the I'm writing it as trans, c e iota exponential k iota k1x. Okay, now if I write down without solving this, what we can write? We can write hk1, the momentum part, and divide by the mass. All right. The momentum, it will be h cross k1 from like, say, whoever has been doing this lectures for continuing following this lecture, now they can directly write it down without even calculating it. Okay, so now in this case we'll define the transmission coefficient. The transmission coefficient. So you see now that whatever physical things we always try to talk about, it reduces to these mathematical equations. Okay, and mathematical derivations sometimes become very involved, and if you are trying to do high energy physics, it's all mathematics. Okay, just to find the initial point, the starting point, and the final point is physics. In between, it's lots of mathematics. Okay, and if you are planning to go for theoretical high energy physics, maybe string theory, maybe particle physics, or uh, okay, cosmology, astrophysics, make sure that you have a good like you are good with maths. Okay, so maths is very important. If your maths is not good, then you should choose something else. All right, so these are just the very beginning. Like I had a friend who is currently a professor in NIT. Okay, he is a string theorist. So he used to get a long register to write down the he used to work on string theory. So just to write the equations, like it used to take a single equation, used to take the whole page, the whole, and he used to specially order big registers, okay, to write those equations. After that, of course, once you are done with that part, you learn the software and try to solve it using Mathematica or whatever is available at that level. Okay, but still, sometimes you have to do the calculation, and each equation, I'm telling you, each equation is like the whole page length. Okay, one equation, it will have so many terms. So this is just the tip of it. Okay, whatever we're doing right now. So transmission, now I'm writing it in short. Transmission, there's no standard notation, but I'm just using it here. Probability current density, or should I write it completely? Okay, let's write it completely, because if somebody is watching this video from the midpoint, it will not make sense to them. So let me write down, this is transmission current probability current density, probability current density. All right, and we have this thing that incident divided by Now I think you get the idea that what you are looking for here. We are just trying to get the ratio of the number of particles being reflected and to the incident particle number. And in transmissions, we are trying to look at the number of particles being transmitted divided by the uh, incident number. Okay, so this is the probability, current, density. All right. Now whatever I write on the screen, I think I have written it correctly, but the software does not reproduce it faithfully. Okay, when I look back again, it looks so bad. So what we have is now this thing, I won't make a box because box is wasting time. So just I'll mark with this star. Now what we get is this is equal to jt, okay, divided by j iota, not iota, sorry, incident. All right. So this is k1. Now what will be left with if you take the ratio? Now you see that there's a k1 here in this region, and the previous region, it was in the first region the k was different, the wave vectors are different, so we'll be left out with these ratios also. Okay, we have these factors, and then we have these factors, which is the usual one. Okay. Now we need to find out now the everything. Now what is there, what do we need? We have the reflection coefficient, which is defined by r. Okay, this is also written as r, not, sorry, not r, this is t. And this the reflection one, this is represented using r, capital R. All right. So what we are looking for is the following. What we are looking for is the following, that we want to calculate r, which is given by mod b square, and this, and t, which is given by k1 k c, and this is a mod square. All right. So this is what you have. Let me have some water. So yeah, so so it everything comes down to this. Everything comes down to solving so much of work, and these are the quantities. Uh, so I often call them cute ones. Okay, because after so much work, you get to these small equations. Sorry. Sorry. Now, in this case, we need to find out. We need to find out. Need to find. Now, see, you don't need to do all these things again and again. Just follow the steps. Like, it's like if you want to go from some place in your city to some place, other place in your city, you don't remember everything. Okay, you don't remember the whole route exactly at each 1 meter. You remember the milestone, the landmarks. All right, where to take a turn, where to turn right, turn left. Okay, and okay, so you just take the steps, the important steps. You take care of the important steps, and you remember, you reach the destination. Similarly, here also, just see how the things have been done. Okay, don't need to remember and rote learn the derivation. Okay, the current probability density was very straightforward. You just remember that you have a sort of, you write down the Schrodinger equation, you take a conjugate, you multiply the alternate, the one equation with the conjugate wave function, and the other one without the conjugate, and you know what which one to multiply it with what, because you are looking for a term psi star psi. All right. Now you just club them together, you get rid of the potential term, and then you finally rearrange and you get the format as we have derived. Okay, so this is how you learn, remember things. Don't try to yeah, you should do it once again by yourself without looking at the notes. Okay, so that gives you a sense of what has been done. Now what we are looking for is b, and C, okay, in terms of A. So if I am able to get B and C in terms of A, we are done. All right, we are done with the things. Now, how to get it? How do we get A and B? Sorry, A, B, and C in terms of A. Okay, so what we have is the boundary conditions. What we have is the boundary condition. We want the wave function, whatever the wave function we have found out, to be continuous everywhere. Okay, to be continuous everywhere. Now, see, the wave functions cannot be normalized. Okay, because these represents that of a free particle. All right. So we know we have seen this, that wave function can be normalized when it represents a bound state particle. Okay, and in this case, there is no bound state possible. All right, because it's a scattering potential, not an attractive potential. And now in this, what we have is psi1 at x equal to 0 should be equal to the wave function in region 2 at x equal to 0. All right, it has to be true because the wave function should be the final wave function. The wave function should be continuous. Should be continuous. All right, everywhere. Okay. Now, what else should be continuous? Now, in this case, since the potential is finite, it's not infinite, we should also have the momentum, which is the first derivative of the wave functions in each case at x equal to 0 should be continuous. Okay, the momentum has to be continuous, which is x equal to 0. All right, so you can see this, that I didn't say this thing, that in classical step potential, what we have was this thing, that we uh, didn't have, when we saw that the energy was more than the potential energy of the system, the particle was able to cross the barrier, okay, easily, without getting back, without reflecting back. But in this situation, when you see a quantum system, even though the energy is more than the potential, even though the energy is more than the potential, all right, I didn't get the potential out here because it's already discussed in the previous lecture, and you can refer to it if you want to. And so in that case, what happened was, we in this case we see that there is a term which, even though the energy is very high, not very high, it's higher than the potential energy, there is a reflection term. Okay, now this is different from the classical thing because of the wave nature of the particle. Okay, this is due to the wave nature of the particle, and it behaves like a wave. Now in this case, we have this argument that momentum of particle momentum of particle should be should be continuous at the boundaries, continuous at the boundaries. Continuous at the boundaries. All right, now this is the now we have this thing. Let's write down the waveform which we had, which is a iot exponential ikx plus b exponential minus ikx. Okay, and x less than 0, and we have psi 2 is equal to c I k1x, and this is x greater than equal to 0. All right, now if we solve this thing, if we solve this, now we are using these boundary conditions and imposing it on these wave functions. So what we have, so using a 1, the first boundary condition, which is psi 1 at x equal to 0 is equal to psi 2. Now this is psi 2 at x equal to 0. So if we drew this, what is the equation we'll get? If we put x equal to 0 in all of the terms, so on this side, on the left hand side, we'll have a plus b, and on the right hand side we'll have c. So this is, say, let's label it 1, not in Roman. Okay, so let's label it 1. Now what else do we have? Now the next one, the next boundary condition, using 2. So I am doing everything for the step potential because you'll get an idea, a feel of what happens in the whole process, and we'll just transfer this knowledge we have gained here to solve the other situations. Okay, we won't derive every time using the Schrodinger equation or the probability current density the way we have derived here. We'll just take this knowledge, the experience which we have in this step potential, and build things from there. And tunneling, quantum tunneling also will do that, the same thing. We'll not solve the Schrodinger equation, we'll just directly write down, because we understand what happens in each of the parts of the potential. Okay, so this is x is equal to 0. All right, so if I write this down, so if you take the derivative, what do we get? If you take the derivative, so we'll, in the first, we'll have a iota k coming outside. Okay, and then putting it x equal to 0, so we'll get this term on the left hand side as iota k into a minus b. Now, and equal to, on this side we'll have k1c. All right, k1c, and this is, say, this is number 2. All right, this is number 2. Now what we can do is we can just take this to be, now there is iota here also, both sides iota will be there. Now what we can do is we can write down a minus b, all right, is equal to k1 by k c. All right, so let's label it 3. All right, so these are the two equations which we have. One is this one. Now you don't need to remember this. All right, these are the things which we have from this boundary conditions. So we see a relationship between ABC in both the cases. Now we'll solve for B and C in terms of A. Now by equation 1 and equation 3, okay, by equation 1 and equation 3, okay, so we are just adding them up. All right, what will you get? So we are adding equation 1 and equation 3. Now why am I writing in Roman? So this is 1, this is 3. All right, now what we get is 2a, okay, is equal to c plus k1 by k c. All right, so if we add them, so we'll get this. Now further, if we solve this, we'll get 2a is equal to c and k1 plus, now if you simplify this thing, what we'll get is, on this side we'll get k plus k1 by k. All right, so this is c already written outside here. Yeah, so this is the form you get, and if you solve this further, you'll get this, that this will be uh, c by a is equal to 2k by, this will be k plus k1. All right, now I shifted my timing in the morning because I wanted to avoid the background noise, but it's the same now again. But it's fine, I have to just work things in the morning. And now by equation 1, now we have solved for c in terms of a. We have relation here. All right, we have a relation here. So this is what we have for c. Now let's solve this equation for, so by equation 1, okay, not this one, that's the other one. All right, we can just substitute this value in that case. Instead of c, what we'll get is this. We have equal to, this is 2, instead of c we'll place this thing k plus k1, which is a. Now this will give us b is equal to 2k is equal to 2k divided by k plus 1 minus 1 a. All right, now if I write this down, b by a, okay, b by a is equal to k minus, now if you simplify this, you'll get this result. If you solve this, you'll get this thing. Okay, now so this is the part you would like to remember for this. Okay, so this is these are the calculations, these are the final forms which you are looking for. All right, so we have got them. Now let's define a quantity. Let's define a quantity, and you need to remember this also. Let's define a quantity which is kappa. Okay, let's call this kappa. Kappa is difficult to write in paper, write on paper, because it mixes up with the k's. All right, so I'll just make this thing funny looking symbol. Okay, so we have 2m e minus v naught e minus v naught divided by h cut case h cut square. All right, so if we divide, we have the other one, this is the k1. Now on this side we have k. Okay, it's like inverted. So if we solve this, if we solve this thing, you'll get kappa is equal to root over 1 minus v naught by e. Now you have to also remember this part, this quantity, how we are defining kappa. So we are defining it. We'll see why we are defining it. It reduces these two relationships, this c by a and b by a, into a form which we already know from something else. Okay, you'll see that uh, coming through. So if we can write this as c by a is equal to 2 by 1 plus k kappa, not k, kappa. All right, and the other one which we get is b by a equal to 1 minus kappa and 1 plus kappa. All right, so this is what we have.
सर इसमें ऊपर 2k था ना?
हाँ वो हट गया ना, एक बार देखो इस पे
ये
अगर
कापा में लिखे हैं आपने? ओके,
हाँ ये कापा में एक्चुअली डिवाइड कर दो इसको, डिवाइड न्यूमरेटर एंड डिनोमिनेटर बाय के, ठीक है, इसमें भी डिवाइड कर दो. So you can write this as this, ना, you can always write this as 2 by 1 plus k1 by k.
हाँ,
Okay, and this converts to 2
कापा.
by 1 plus kappa. Okay, and in this case also, if you divide this thing, you have 1 by k1 by k, and you have 1 plus k1 by k. Now you can write this as, you can write these as equal to 1 minus kappa divided by 1 plus kappa. So I thought it was obvious, so I didn't do it. Now I have done it. Now what we are doing is we are trying to calculate r. R was b by a. Okay, r was b by a, which is mod square. This is 1 minus kappa, 1 minus kappa plus 1 plus kappa. Okay, so we have this mod square. Okay, now this number, this kappa, is a real quantity, so we can simply write it like this. Okay, and if you write this down, that you have a t, okay, t is k1 by k, and this was c, okay, this thing is equal to kappa, and inside we have 2 by 1 plus kappa, 1 plus kappa. All right. Whole square is equal to 4k by 1 plus 1 plus kappa whole square. All right. Now, in this case, what we have is r plus t. If you see this, if you do this thing, if you add r and t, what should we expect even without calculating?
1.
It should be 1, right? Now, this is obvious because the total probability remains constant, okay, and we see if we calculate, if you calculate using this these two, if you whatever result we have, we'll get 1, okay. So I'll just write it this thing, that 1 minus kappa square, not this way, this is so this is 1 plus kappa, okay. So my k's and kappas become same, so make sure that you get it right, okay. This is what we have, and this is 4 kappa, this is 1 plus kappa, okay, which is square. Now let me highlight this.
Sir, t is equal to 2 kappa whole square.
यहाँ पे मैंने स्क्वायर क्यों करा मेरे को पता नहीं. I shouldn't have done a square here. This is the thing, we have a square in the bottom. You're right. All right, so this is what you want to take back home from this whole exercise, okay. This is the obvious, that the probability remains same. Now let's analyze the situation. Let's analyze what is happening. What can we get from here? So let's say if I increase E, let's say we increase the energy of this thing, the particle. Okay, it's already higher than the potential. Let's say we increase the E. If we increase the E, what happens to kappa? What happens to kappa? So the kappa is related to, equal to, this is 1 minus V naught by E. So this E naught by V reduces.
Increases, energy increases.
So energy increases. What happens to kappa? So energy increases, the kappa
Increases.
now V naught by E. Okay, this the pen tablet is not reliable at this time anymore. Now, if we increase this, so V naught by E decreases. All right, and what happens to kappa? Kappa increases. All right. So what happens to T? What happens to T? Anyone?
Decreases.
The T also increases. Okay. T also increases. If you can see, if you can compare this numerator to denominator, you can understand this thing. All right. So where this is 4 times that. All right. And if you see that this value of kappa will always be less than 1. The value of kappa will always be less than 1. All right. So if you do this take a value of any kappa, if you take a value and then change it, okay, say let's you take it to be kappa is equal to say 0.1 it was earlier, and then you take it to be 0.01, okay, 001, and you can see what happens to t. All right, so the transmission increases, and it's physically also viable, because you can think of when the energy increases of the particle, the probability of getting transmitted will automatically increase, even if you don't do the calculations. Okay, so you can look at up how this is behaving. Now energy increases, this ratio decreases, kappa value increases. All right, and this the transmission coefficient also increases. Now if next one is, if next statement is, if E of incident wave, okay, E of incident wave, if E of incident beam, not wave, we're talking about beam, is too high, is too high. All right, now what will happen, this E is very greater than the potential. Okay, the potential. Now what happens here is, then the potential will be, then the potential will be then the potential will be very weak compared to the energy of the beam to affect the particles. Now to affect the particles, it means the trajectory of the particles. Okay, and it won't be affected much. All right, and what we see here, what we see is kappa is equal to 1 minus v naught by E. Now if energy is very high, so this will be almost equal to 1, and if you substitute this, T becomes 1. All right, so, and if you have, if the energy decreases, if that energy decreases, that means the transmission coefficient will, this thing will also will decrease. All right, the transmission coefficient also will decrease, because it will be the beam will be closer to the energy of the beam will be closer to the potential energy, and the potential energy will be strong enough to affect the particles. All right, so, and if I say that E is tending to v naught, all right, if it's very close to v naught, what will happen? T, if you put v naught equal to E, in this case kappa will become 0. Now transmission coefficient will tend to 0, and R will tend to 1. All right, and here kappa is tending to 0. If this happens, kappa is tending to 0. All right, and T tends to 0, and reflection becomes 1. All right, if the energy of the beam is very near the potential energy, very close to it, then the reflection coefficients become 1 and the transmission coefficients become 0. So there is no reflection at all. All right, no transmission at all. All right, so this is the analysis which we have here. We'll discuss the next case, which is E less than V naught. What happens now? That situation will be interesting to look at. Okay, now quantum mechanically, classical mechanically, if we have energy of the particle less than the potential energy of the target which we have, it will of course rebound. It will come back. It is obvious. Okay, any child can tell that thing. All right. But what happens in classic quantum thing is that we see that there is the probability is very low, but there is a probability, there is a chance of the particle entering the barrier. All right, so we'll look at it in the next class. All right, so any questions, any comments? So let's stop here. Thank you for watching. Have a great day.
Thank you, sir.
Take care.